and journals, IEEE transactions on PAMI, IEEE transactions of instrumentation and measurement, Journal of Parallel and Distributed Computing, IEEE or ACM transactions on computational biology and bioinformatics, Elsevier information science. Now, I will request Sir to start the session.
Hello. Yeah, thank you very much, madam, for the introduction, for the kind introduction. So, okay, actually, I have one request. I'm not able to. Okay, I'm able to see the chat now. Okay, so fine. So what I will. Okay, so let me first share my screen. Okay, so is my screen visible?
Yes, sir. Yes, sir.
Okay, and okay, let me switch on the arrow. So the pointer is also visible, right? The pointer on the screen is also visible.
No, sir.
Okay, now it should be visible.
Yes, now it is visible.
Okay.
Yes, yes.
Okay, thank you very much. So, okay, so thank you very much, everyone, for giving me the opportunity to talk to you. So, I have slightly changed the title of the talk, and as many of you know, one of my one of my areas of interests is this scalable techniques for machine learning, or machine learning using big data. Okay, just 1 minute. Yeah, just give me 1 minute. Let me just switch off. Okay, yeah. Okay, so so I thought today I will yesterday I was talking to Professor Maiti. So he was. Hello. Okay. So yesterday I was talking to Professor Maiti, and he assured me that most of the people on this class are actually faculty members, and I thought maybe you are interested in my this research area of how to develop scalable techniques for machine learning, and in general, and scalable techniques for so many machine learning algorithms. Okay, so that is what I will be talking about. So the other thing is, I typically like my session to be very interactive. So I just wanted to ask, what is the mode of interaction? Is it so? One thing is, I can
both microphone and chat box participants can use.
Okay, thank you. But actually, in my screen, I am not able to monitor the chat box because my whole screen is, about this this slides. So,
Sir, I will notify. Sir, I will notify if some message comes.
Yes, yes. Thank you very much, Professor Maiti. So, if somebody can just notify, and I will request the. So I have a lot of things to say, but my idea is that it will be best if I say fewer things, but a lot of people are understand and appreciate, and they are able to so they are able to take away something from this lectures. Okay, and yeah, so these are active areas of research. So there is also possibility of some collaboration if any of you are interested we can also think about possible collaborations. So with that, I will come to our first, and this is kind of the project that I am most actively working on now, and this is about autonomous driving. So I don't know. So most of you probably know about what is autonomous driving. So autonomous driving is basically the idea that there should be a computer system which should be which should be sitting in either a car or it could be something like mostly it has been tested on cars, but there are also other applications, like it could be a mining vehicle, for example, or so some sort of automation in mining operations, or it could also be a something like a warehouse automation. Okay. But for this talk will mostly be focused about autonomous cars. Okay, but there are many applications of autonomous driving outside autonomous car. Okay, so so with this, so I will talk about this, and so the idea is that we have to develop this, the system where a computer algorithm can present or can sort of take at least part of the driving decisions itself. Okay, so for example, there are various levels of autonomous driving, as many of you might know. There is level 1, level 2 till level 5. So level 5 is completely autonomous. Okay, level 4 is autonomous but with presence of driver, and level 3 is partially autonomous. So partially autonomous systems is what you sometimes see where in some advanced vehicles today, where for example, if there is a car in front of you which is very close to you, so the system may apply the brakes, okay, autonomously. So the system may sense that there is another car or another pedestrian who is just in front of you, and maybe due to some reason you are not able to press the brakes fast enough, so it will brake instead of or for you. So it will apply the brakes even though you have not actually pressed the brake in the car. Okay, so this is, for example, one application. Then there are lane change assists. There are back out assists. Okay, so if you are, let's say, backing out of a parking lot, you will sometimes see in the roadside dhabas or hotels, there will be one person, a security guard, who will signal you that you can now back out of this thing because there is no traffic coming through the highway. Okay, but what if that security guard is not there? It is very difficult for you to see whether the traffic is coming or not. Okay, so that can be another assistance that can be provided, that it can signal you when it is safe to back out. Okay, this kind of systems are there, and okay, so now the idea here is that training. So most of these autonomous driving systems use some form of machine learning. Okay, usually they use deep neural networks. Okay, so I am assuming here that all of you are familiar with deep neural networks. Okay, so so now deep neural networks take for complicated tasks like autonomous driving, they take a lot of data to train. Okay, so it is very data intensive. So here are some numbers. So you can see that okay, you can see that so for example, Waymo. So this slide is from about 1.5 years back. So at that time, so by the way, Waymo is Google's autonomous driving. So now, earlier Waymo was a independent company, but now it has been acquired by Google. Okay, so so 25,000 autonomous miles per day. Okay, so Waymo has test cars which drive 25,000 autonomous miles per day. Okay, and so they have driven about 5 billion miles. So they have data for 5 billion miles worth of car driving. Okay, and the data is something like it takes about 750. So it takes about 750 megabytes or megabits in this case to store about 1 second of driving data. Okay. Now consider this futuristic scenario that you want to start a startup company, or you want to design these kind of self-driving systems. Okay, so you have a car in which you can put some sensors, and the sensors, so the sensors are typically camera, sometimes they are lidar, but we have mostly worked with camera. Okay, and so these sensors, they they yeah so they gather the data, but then the sensor is in car, and the car cannot host the server which is training the deep learning model. Okay, so the card is called the edge. Okay, in IoT literature or Internet of Things literature, the card will be called an edge device, and server which is present in some data center, either on premises or one of the clouds or something, which will be called the core. Okay, so edge to core data transfer is required, because all this data is needed to be transferred to the core, where it will be trained using using self-driving technology. Okay, now so so the raw data collected is about 1440 megabits per second. Okay, so this is if you are trying to collect, let's say, a 2 megapixel data with 24 bits per pixel and 30 frames per second. Okay, so I am estimating this slightly on the higher side. Maybe you can do with 700 or something Mbps, but I'm just estimating it to be 1400 to be safe. Okay, and now the data compression that you can get using MPEG is something like 70:1. Okay, so the bandwidth that you need is something like 3.9 Mbps. So suppose you have 100 cars like this. Okay, then you require something like a 390 Mbps. Okay, now suppose you have something like a 10 Mbps bandwidth. Okay, this is a very large bandwidth even today. Okay, so this is large because you are requiring, and this is megabytes per second. So this is actually 100 Mbps, something like 80 Mbps to 180 Mbps, if you are counting megabits per second. Okay, so this is still a very large transfer rate. If you want something like a sustained, if you want a sustained, so such transfer rates can be sustained in bursts, but not sustained over a period of time. Okay, so roughly I have put here a number, something like 39:1. Okay, so instead of 39:1, you may even try something smaller, something like 20:1, or even smaller, like 5:1 compression ratio. Okay, so this kind of compression ratio is required. Okay, now how do you compress data? So before this, I just wanted, so maybe some of you will be interested in the experimentation framework that we use. Okay, because such kind of experimentation in an academic is expensive. So Google and others, they can actually run cards on the network, but as academicians we don't have typically the funding to do so. Okay, so we have to use some kind of a simulator framework, and many simulator frameworks exist. So for example, there's a simulator Torx, which is something like a game. Okay, there is so this is in the top right. Okay, then there is the Udacity self-driving simulator. Okay, which is there in the bottom left, and then there is the Grand Theft Auto, which is also a game. Okay, and it also has its simulator. I mean, you can use it as a simulator environment. So what does the simulator do? The simulator will basically drive the car in the virtual environment, which you can see here in the pictures. It will collect the video of the driving. Okay, and then it will take that video and try to train these self-driving car models. Okay, so but these have some problems. Okay, I am not going too much into details of the problems, but the problems could be, for example, something like the simulator only works in a or the environment that is provided is only in a hilly area or inside a stadium where there is a race going on. Okay, or sometimes it is just that, for example, with GTA 5, so the simulator is very realistic, but there is no benchmark policy, or there is no feedback for violation of traffic rules. Okay, so these things are not there. So around I think 2017, Intel announced their simulator. So this was Carla simulator, which was developed by Intel and EPFL in Europe, and this supports. So this is a software that supports training and validation of autonomous urban driving systems. Okay, and it is an open source software which supports both training and testing protocols. So you can collect the data from the simulator, and then you can do training, and then you can deploy the trait policy into the simulator and then test it out. Okay. So there are a lot of maps, okay, where you have different layouts, and also there are various environmental conditions. Okay, so like it can be cloudy, rainy, sunny. Okay, and also you can sort of control the kind of traffic that you have and the kind of pedestrians that you have. Okay, yeah, and it also supports different kind of sensing or sensor suits, they call it. So you can have one camera, you can have 3 cameras. Okay, you can have you can have LiDAR also, and all these things. Okay, yeah, so this is an image that you get. And basically you have your so the background image is the camera view that you get. Okay, then you can get the depth map. So the bottom left image is the depth map that you get. Basically, it is something like the farther the thing is, the more white it is, and the closer something is, it is more black. Okay, uh, and to the right is what is called the semantic segmentation image. Okay, so semantic segmentation is basically a segmented version of the image where you have, for example, you can see here the road is in purple color, the houses are all in gray color, the sky is in black color, and the fence is in blue color, and the center lines, which is very important, is in yellow color. Okay, so and this is actually from our driving setup. So this is a still from our driving setup. So we also have videos which I can show if someone is interested. Right now I have not put it. And we will come to what affordances are. Okay. Now the question really is, how do we reduce the data that we collect? And the way to reduce the data that we collect is via what we call the frame subset selection. So you know that each video can be divided, is a sequence of multiple frames. Okay, so each video is a sequence of multiple frames. Okay, and typically you can think that from one frame to the other there is not much difference. Okay. So the question is, how can we reduce the frames? Okay.
Sir, one participant have already asked one question.
Yes.
Please explain the difference of longitudinal segmentation and CARLA.
Longitudinal segmentation and
CARLA. CARL in capital.
CARLA is a okay. There is nothing called longitudinal segmentation where I don't know where they got the. So there is nothing called longitudinal segmentation. So CARLA is a simulation platform. So I hope this is clear to everyone. Okay, it is a simulation platform. So CARLA is a software. Okay, so what does the software do? The software, as I mentioned, it allows you to capture the videos. Okay, and then using these videos and some feedback which we will come to, it allows you to train the model, okay, the driving model, and then it sort of it allows you to take the trained driving model and run the car again in that framework. Okay, and you can check how well the car is driving. So whether the car is bumping into things, whether it is going straight, whether it is able to take the turns correctly, and all these things. Okay, I think you are talking about this longitudinal model here. So this longitudinal model is the driving model. Actually, there are two parts to the driving. One is the acceleration and the brake. So these are called longitudinal model because you basically you go straight along the longitude of the car in some sense. Okay, and there is the other part which is the steer. Okay, so steer is basically to what angle do you want to turn. Okay, So these is typically called the lateral model. I hope this is clear. Okay. Okay. So just to impress upon you, the whole driving model is a very complex architecture, and it is and there can be many different architectures for the driving model. Okay, so sometimes one of the components is this semantic segmentation, which takes the semantically or rather the normal image as input, and it outputs the semantically segmented image. Yeah. So, for example, just to understand this, suppose you have as input this H cross W. H is height and W is width, cross 3 image, or you can also have a grayscale image, but typically we work with RGB images. So you get H cross W cross 3 image, and each pixel is classified among C classes. Okay, so the output is H cross W cross C. Okay, where the C is basically the number of classes, and each sort of dimension there is indicator of one of the class. So typically, I think in our case we use 12 classes. Okay, so one could be like houses, roads, ground, trees, fences, lampposts, etc., etc. So so the one there indicates that basically you have that particular pixel is denoting a house or is part of a house in that scene. Okay, so that is what the semantically segmented image shows. And again, here there is a sort of an example. You can see the cows, and in the background there is the ground, there are the trees, and there is the sky. Okay, so you can see that this blue part is sky, this pink part is trees, and this green part is ground. Okay, and this brown part is the cow. So every pixel has one of the colors. The colors is here in this image, semantically segmented image, is denoting the class. Okay, so and then what you have here is you have a model, typically a deep learning model. So we use something called DeepLab V3 Plus, which is a very good and very well-known deep learning model for computing the semantically segmented image given the input RGB image. Okay, so okay, so now so the question is, how do we reduce? So one of the techniques which we tried is what is called Godek plus CUR decomposition. Okay, so what is Godek? So Godek takes your so Godek is an algorithm which is basically a three-dimensional algorithm. Three-dimensional algorithm in the sense that it takes the entire video as the input. Okay, so it takes the stack of frames as the input. So it will take a segment of the video as the input. Okay, and then it will decompose it into two components. One is the low rank component. Okay, so the low rank component is basically the one which is kind of how should I say, like it is the component which is somewhat stable across time. Okay, or it stores, it may have many different frames. Okay, but these different frames will store the different low rank components, or the different how should I say, temporally stable frames across time. Okay, whereas the other part is the sparse part. Okay, so the sparse part here will store the changing part of the video. So the hope here, so the low rank component is of very low rank. So if your original stack of frame matrix is of size, let's say, something like maybe 10,000. So let's say your original frame is 100 cross 100. So basically you flatten it into 10,000, and then suppose you have let's say 1,000 frames. So 10,000 cross 1,000 matrix. It will reduce it to something like a 10,000 cross. So the matrix will be 10,000 cross 1,000, but it will be a very low rank matrix. So many of the rows will be repeated. Okay, and the sparse thing will have a lot of what should I say, a lot of entries. Okay, so it may have a high rank. Okay, but it will have a lot of zero entries. Okay, so you can just code it as a sparse matrix and send. So your total data transfer will hopefully get reduced by this. Okay, now so the sparse thing can be sent in a sparse manner, but how about this low rank part? Okay, so in order to actually reduce the data transfer of the low rank part, we further decompose this using what is called a CUR decomposition. Okay, so what is CUR decomposition? CUR decomposition is again writing a large dense matrix like L, but low rank matrix, into this form where you have it. This L can be recovered as a product of three matrices C, U, and R. Okay, C is, so let's say L is of M cross N size. Okay, so C, and it has a rank R. Okay, so here M and N could be in thousands, like I mentioned, but the rank R could be only maybe tens, a few tens, maybe 50 or something. Okay, so your matrix C is M cross R, your matrix U is R cross R, and your matrix R is again this capital R is again R cross N. Okay, so this is the CUR decomposition. So this is something like a singular value decomposition. For those of you who know singular value decomposition, this is something like a singular value decomposition, except that now these columns, so this C is something like a matrix of selected columns. Okay, so these are actually columns selected from this L matrix. So this basically gives you the subsets of frames which are to be selected. Okay, so this section shows the reconstruction errors of this approach. Okay, so this slide rather shows the reconstruction error of this approach. So you can vary the rank. So you can take the rank as maybe 5 or 10, and uh, then you can select a certain number of frames. Okay, so so I think we started with about 100 frames. So 50x reduction is something like where you get 2 frames. 11x reduction is where you get 9 frames, and 6x reduction is where you get 17 frames. So probably in this 11x reduction, so we are getting something, a reconstruction error of around 0.35%. Okay, so this is a very low reconstruction error. So this is a technique which we can use. Okay, but there is a problem. Okay, what is the problem? The problem is that you see, you have to process this stack of frames matrix, and this stack of frames matrix is very, very large. Okay, uh, and this algorithm, for this Godek algorithm and followed by this CUR decomposition algorithm, is very, very compute intensive. Okay, and there is no simple online solution to this also. Okay, so how can we how can we mm, uh, so that is why this approach is not feasible. Okay, for that reason. Okay, so yeah, so in our experiments, it takes about 30 minutes for compressing 100 frames. Okay, so if you are going at even at 20 frames per second or something, this is just 5 seconds of video. Okay, so it is taking 30 minutes to compress 5 seconds of video. Okay, so then what we started, and also the other problem with the previous approach is that we cannot incorporate signals from the already trained model. So in many real life case, we will have an already trained model. Okay, and we want to see if we can get the performance to be better by getting newer frames. Okay, so for this purpose we came up with this incremental subset selection approach. So what is the incremental subset selection approach? Here you have a cumulative set, which we are denoting by CT. Okay, which is the set of all frames, okay, that you have seen till now. Okay, and XT is the set of all frames that you will see from now. Okay, so CT plus 1 is the set of all frames that you will see in the next time set. Now, suppose you have already constructed a reduced set, which is, we are calling it RT. Okay, so you have a reduced set RT, and you are able to somehow, let's say, construct a reduced subset of frames X SB. Okay, so X subset T. Okay, then you can take the union of all these frames and you can construct the reduced set for the next timestamp. Okay, so this is the framework of incremental subset selection. Okay, and as I mentioned that you can take many different metrics. Okay, so what are the metrics you can take? So we have taken one metric called SIFT. Okay, SIFT is a measure of perceptual similarity between two frames. Okay, so this is a pairwise metric of perceptual similarity between two frames. Okay, then there is the metric of the semantic segmentation loss, or whatever model you are trying to train. the loss from that model. Okay. Then there is the metric of distinctiveness, which is a metric that you derive from the deep learning model itself. So it is a measure. So you have a deep learning model. So the way the deep learning model works is that you have many layers, and each layer has some activation values, right? So these are layers of neurons, and each layer has some activation values. Okay. So distinctiveness is a model of is a measure of difference in model activation values, uh, and so basically this is kind of like a label agnostic way of trying to measure how much a particular model can or a particular example can improve the representation quality of the network. Okay. So this is the distinctiveness value. The other value is called the uncertainty value. Okay. So this is a measure of how much confusion is there in prediction of classes. Okay. So again, this is a label agnostic measure because both these two measures are designed for active learning setting also. Okay. So similarly, SIFT is also label agnostic, but semantic segmentation loss is not label agnostic. Okay. So these three measures are the ones which can be used for active learning setting. Okay. Now these measures, distinctiveness and uncertainty, were first proposed in this KDD 2018 paper. Okay. But this was proposed for a small number of classes. Okay. But in our case, in the semantic segmentation case, each pixel is a class. Okay. So since each pixel is a class, then you have to so we had to appropriately modify it to give us the correct type of metric. Okay. Okay. So now comes the formulation. So now, given that you have all these metrics, okay. So here the metric that you have are, you have this. So let me maybe denote this. So you have okay. Yeah. So you have the loss metric, you have the distinctiveness metric, okay, and you have this one, which is the uncertainty metric. Okay. And you have here what is called the I'm sorry. So this is the shift dissimilarity. Okay. Dissimilarity. So this entire metric, so if oh so yeah yeah, so this is your final final dissimilarity metric. So combined dissimilarity metric. Okay, so this is the combined dissimilarity metric. Okay, now what we are doing here, so so the others are coefficients. So eta 1, eta 2, eta 3, these are coefficients. Okay, and this q is basically going into here. Okay, so we have the pointwise metric. Okay, and which is the qi. Okay, and we have the pairwise metric, which depends on pairs of frames. Okay, and that gives us the overall dissimilarity metric. Okay, now what is this overall dissimilarity metric doing? Okay, so this overall dissimilarity metric is basically so you see here there are sorry, okay, let me put now this one. Okay, so you see here there are two things. Okay, one is called Zijo, another one is called Zijn. So like I mentioned, there are two sets. Okay, one is this RT set, which is the set of existing selected examples. Okay, and there is the M set, which is the set of incoming examples. Okay, now Zij is basically so Zij is a 0-1 variable. So you can see it here. Both the Zijs are variables between 0 and 1. Okay, so the way to understand this Zij is that Zijo is the indicator that the new frame I has the representative old frame J. Clear? So in general, it is something like this, that Zij is basically saying that your J is representative of I. Okay, so this is what it means. Okay, so it means that so if it is O, then it means that jth old frame is representative of ith new frame. Okay, and if it is Zijn, then it basically denotes that jth new frame is a representative of ith new frame. Now, and then we are trying to minimize the total dissimilarity. Okay, so what does this mean? So I will come to the second term in a minute. Okay, so I will come to the second term in a minute. But these first two terms in the objective function, what does this mean? So this means that you select the dissimilarities for select the representatives for all the ith new frame among among either the old frames or the new frames. Okay, and you select the ones which have minimum dissimilarity so with I. Okay, that is what this part of objective is doing. So it is asking you to select, it is basically allowing you to select the representatives for all the new frames which are denoted by the index j. Okay, in such that the total dissimilarity between the representatives and their original frames is minimized. Okay, Now, what is this part doing? The second part of the objective function. The second part of the objective function is saying that it is taking all the representatives which are there in the new frames. You see, only the Zij ends are taken, okay, and it is taking the norm of them. So this is basically, in some sense, that how many representatives have you chosen from the new set. So what will happen at the end of it is only the representatives of the new set will be taken. All the other frames will be dropped. Okay, so from the new set, in the existing set, you have already the compressed set, which is RT. Okay, if a new frame has a representative in the old set, then nothing needs to be taken. But if a new frame has a representative in the new set, then only the representative will be taken. The new frame will be dropped. And this second term is a measure of how many representatives are there from the new set. Okay, so you are also minimizing the number of representatives which are there in the new sets. So there is a weighted objective, lambda is the weighting factor. So if lambda you set to, it is a factor that the user gives as input. So if you set lambda to 0, then there is no penalty for selecting a large representative from the current set. But if lambda is very high, then you have a lot of penalty for selecting representatives from the new set. And now what is the third equation or constraint doing here? It is just saying that every new example will have exactly one representative. So Zij-O and Zij-N, when you sum over all the J's, that is all the possible representatives, they should sum to 1. So only one of them should be selected. Okay, so this is what this formulation is doing. Okay, so I hope the formulation is clear. Okay, and now I can give you some results. So basically, so we have some baseline methods. One is so by the way, here there is so your objective, remember, is that when you train using the selected set, okay, the model, then you should be able to your total your test error, okay, should be minimized. Okay, your test set error should be minimized. So so these are some of the baselines. Okay, so one of the baselines is the one that just involves distinctiveness and uncertainty. Others are random, and another baseline is cumulative, where there is no data reduction. Okay, and we compare this with the following method: shift only, shift plus loss. Okay, shift plus distinctiveness plus uncertainty, and the whole set 6. So this SDU and shift are both active learning methods, and SL and SDUL are basically dependent on the level. And we can see that for 100:4 compression ratio, okay, there is a drop of, so cumulative is your baseline, and you are getting this accuracy and mean IOU, okay, and your accuracy is something like here. So here it is 85%, 86% maybe, and it has come down to more like closer to 85% here. Okay, so if we are using SDUL, whereas if you are using, let's say, only shift, then the drop is about 1.6%. okay, and it comes down to almost 84% here, okay, and the others are like this, okay. Similarly, you can see the number in the bracket. So if you are using 100:9, so you select 9 out of every 100 frames, you get a drop of about 0.6. And if you select 15 out of every 100 frames, you get about 0.5. So maybe, you know, this 11x reduction, this 9 out of every 100 is kind of a good reduction, okay. Okay, so now, so any question on this part? Okay, so now I am just going to describe the autonomous driving model. Okay, so uh, so there are, you know, various types of autonomous driving models. Okay. So some of the older ones. So I'm just going to go quickly over the literature review, okay? Because this is not very recent and also not very, I will say, not very interesting. So broadly, there were the modular pipeline approaches where, you know, people used to design like a semantic segmentation model for the, so there used to be this perception stack, okay, so there used to be many different algorithms.
One question is there.
Yeah, please. Yes.
Has there any role in row value in formulation problem?
In the row value, yes. Okay, so thank you that you asked. Okay, so here the row is basically selecting the weightage you give to shift. Okay, so if row is 1, then it is shift only. So the way we select these methods is by varying these rows and etas. Okay, so if row is 1, then it is just the shift model. Okay, if we want to, so eta 1 plus eta 2 plus eta 3 should be equal to 1. Okay, so if we want, let's say, only shift and then distinctiveness and uncertainty. Okay, so I will set eta 1 to 0, and let's say I am giving equal weightage to distinctiveness and uncertainty. Then I will set eta 2 to 0.5 and eta 3 to 0.5. So that is how we select it. Is it clear?
There is another question from the same participant. Can you look for a row optimal value?
Yes. So very good. So can we look for a row optimal value? Yes, indeed we can, and we are working towards that. There's a problem there. So the problem is that row optimal for what, right? So what you really want, so you know, you cannot take the training set loss because, I mean, I don't know if you can if it can be interactive. So can anybody think why you cannot take a row optimal or eta optimal using the training set loss? Okay, so I don't know if they can talk. So I will just give the answer. The answer is, you see, the loss is already here. Okay, so the optimal for training set loss will be what? Rho is equal to 0, eta 1 equal to 1.
One answer given with some objective measure in constraint scenario.
With some objective measure in constraint scenario.
Yes.
Constraint scenario. Okay, I am not sure I understand the answer. Okay, let me describe the answer. So here, the simple idea is that you already have loss as the signal. Okay, so basically, if you try to minimize the training set loss, okay, then what will happen? It will select rho to be 0, eta 1 to be 1, and all the other etas to be 0. So that is the optimal. So we know the optimal solution, because if you want to, if you want to minimize the training set loss, okay, then from the new set you select the examples which have minimal loss, okay, and include them in the training set. Okay, so then what will happen is that you will have a training set which is more compliant with each other. Okay, but that is not what you want. Okay, so you can select. So it is a good ask to select row which is optimal, but optimal with terms of what? So the next thing comes that maybe it should be optimal with respect to validation loss. Okay. Now, if that is the case, then it is possible to solve for that, but the resulting problem is no longer a convex optimization problem. Okay. So another thing I forgot to mention here, probably I should mention it here, is that this formulation, okay, so this whole formulation, an attractive approach is that this is a convex optimization problem. So we are also trying some non-convex formulations, but there you have much more choices. But there the problem is that you are never guaranteed optimal solution. That is one problem. The other problem is that, see, people have been studied convex optimization for a long time, and there are very, very good generic convex optimization solvers. So we have used, for example, CVX, okay, and it is very fast, okay, because people have developed, in the optimization literature, people have developed many very fast algorithms for solving convex optimization problems. Okay, but if we have to develop the algorithm ourselves, then it is not so sure. So that is another thing. Okay, so I hope that clarifies the doubt. Okay, but that is a very good question. Okay, so and we are kind of trying to do something on those lines also. So, okay, so now we come to this modular. So these are the existing approaches for autonomous driving. So one is modular pipeline. So mainly this is something like, so I have given the references here. So this is a very complex pipeline. Okay, this is a very complex algorithm that people have set up. Okay. So then with the advent of so complex algorithm, as you can understand, it has its own problems. If any of the components fail, then debugging is a problem. All those things, the debugging and maintenance of the whole system, then incorporation of new data. All those things are much more expensive. Okay. So what did deep learning do? Deep learning said, you don't have to build all these complex modular pipeline approaches. You can just do end-to-end learning. So end-to-end learning means that you don't have to do all these separate semantic segmentation algorithms, separate object detection algorithms, separate pedestrian detection algorithms, separate traffic light detection. You just, all this information is there in the input image. So you just take the input image and you directly output the controller actions. So controller actions are basically brake, throttle, and steer. Okay, so you directly do that. And again, this approach was sort of tried out by couple of folks at NVIDIA. So NVIDIA people, they had this GPUs, and one of the major applications they were saying is autonomous driving, because GPUs are highly parallel and they could do this autonomous driving processing in a parallel manner very fast. Okay, so so they did it, but it was successful to an extent, but not greatly. And the reason is that there is not much control. Okay, so you have a huge neural network. Okay, it takes a lot of time to train. Okay, it takes in a lot of data, and you use a very powerful computer to train it, and a very powerful computer to execute it also. Okay, so for executing the controller on the car, you may use a GPU. Okay, but for training also you will need to use GPUs, but many of them. Okay, because you need to process a much larger volume of data. Okay, and so anyway, so it turns out that it is hard to train such end-to-end learning models, and it is even harder to debug such models. So suppose you train, and then on a particular frame there is an error. Okay, you don't know why the error is there, so there is very little explainability. Okay, so okay, so this is also end-to-end learning. Okay, yeah. So end-to-end learning, people have done a lot. Okay. So here I want to mention something. Okay. Yeah. So then came. So actually, I'm calling this end-to-end learning because this is an end-to-end learning framework. But this class of methods is kind of called affordance learning. Okay, so this is the kind of approach that we take. So what is affordance learning? So affordance learning says that you don't directly learn the controller action. Okay, instead you learn some high-level commands from the image. So for example, this is more closer to what humans do. So high-level commands can be, let's say, you may say that turn right, okay, or go straight, or stop, okay, things like this, okay, and from that, so once you have the high-level commands, the next stage is actually very simple and predictable. So people have what are called these controllers. Okay, so in the control theory literature, people have developed controllers which takes these high-level commands, and they can generate the control signals. Okay, and these controllers can be learned, or they can also be some sort of static controllers. Like there are signal processing based controllers, nonlinear signal processing based controllers, like the PID controllers, feedback controllers, all these kind of controllers. The advantage of these controllers is that their stability behaviors is known. Okay, so if you can, let's say, you generate a command like go straight. Okay, you know that the controller will stabilize itself. Okay, because that analysis has been done. Okay, but the neural network model, it may keep getting faster and faster and faster speed. Okay, and it may not be able to, it may go too fast or something like that. Okay, so all these things are not predictable, but in case of a controller, these things are predictable. Okay, so so this is kind of the most accepted paradigm now, that instead of predicting the actual controller commands, you predict some high level affordances. Okay. And there have been many of these. So there have been so the next part is something called conditional imitation learning, where what you do is not only do you learn the affordances, okay, or rather I should say this conditional imitation learning is the other side of it, where it predicts the driving action, okay, but it predicts it via a conditional network. So what is a conditional network? Conditional network is where you also give an input driving signal. So you may say, for example, from the planar module, so at a particular intersection, you may want to go left, okay? Or you may have a planar module which says that, the car in front of you is not moving for a long time, okay? You want to actually take your own car into another lane, okay, left lane or something, and then you want to go. So the planar module will generate the waypoints accordingly. And these waypoints will be input to your affordance learning module. Okay, or yeah. So let me come to the conditional affordance learning directly. Okay, so what does conditional affordance learning do? Okay, so you have your agent. Okay, now you have this perception module plus this directional commands, like I said, and these directional commands could be coming from a route planning module. Okay, so like I said, a planning module could be giving you the waypoints as to where you want to go. Okay, and your perception module is just the neural network that we talked about. So it takes the camera image as the input. Okay, and this whole thing is fed into a neural network model. Okay, which predicts the affordances. Okay, and from the affordances there is a control module. Okay, which will directly predict steer, throttle, and brake, and then you can test using the simulator. Okay, so this is kind of the architecture in which we work. Okay, so so our job is basically to train this neural network model. So so this is how, so what happens is that to the route planning module. So this is something we don't work on. So this comes with the Carla. So the Carla simulator also gives you a route planning module. So if you have a pair of endpoints, origin and destination pair, okay, Carla will generate the the route planning module will generate the intermediate waypoints. But like I mentioned, your intermediate waypoints can also be generated by some other module, like in case of robot navigation and all these things. You may have seen that these intermediate waypoints are generated. There are actually planning algorithms which explore the environment and also generate the waypoints accordingly. Okay, so there are so that is another problem which we will not discuss here. Now, what are the affordances that we learn? Okay, so the affordances that we learn are so there is the hazard stop. So hazard stop, it takes two values, true or false. Okay, so the hazard stop is true when there is a person in front of you. Okay, otherwise it is false. Okay, or even if there is a car, it will still be true. So either there is a person or there is another car. Okay, it will be true. Okay, then there is the red light. So you have to predict whether whether there is a red light or not, and basically whether the red light is true or false. So if there is a red light and the signal is red, then it is true. Otherwise, it is false. So it has to detect whether there is a red light, and if there is a red light, it should detect whether it is actually red or it is green. Okay, if it is green, then also it should predict false. Okay, then there is the speed sign, which is which is basically it says whether there is a speed sign or not, and if there is a speed sign, then what is it? Is it 30 kilometers per hour, 60 kilometers per hour, or 90 kilometers per hour? Okay, so what is the speed limit? Okay, and then there are three more continuous affordances. So one is distance to vehicle. So it is basically the distance to the vehicle in front of you. Okay, uh, and if the vehicle is very far away, you just predict 50. Otherwise, you predict the actual distance. Okay, and yeah, if you are very close, then you predict 0. Then there are the two steering related affordances. One is called the relative angle to the center line. Okay, so like I mentioned, so it is expected that the road will have a center line. Okay, and now this particular affordance will predict what should be, rather what is your relative angle to the center line. Okay, uh, and the last one is distance to the center line. So how far is your vehicle from the center line? Okay, so these are the affordances, and here in the interest of time I will not go into the detail of how you can get this from the simulator, but there is a bunch of calculations that you can do in order to get all these affordances from the simulator. So I will skip this slide. Okay, now comes our conditional affordance learning model stack. Okay, so by the way, this conditional affordance learning model was developed by a group in EPFL Europe. Okay, so the original conditional learning model was developed by a group in Europe. I think I have given the reference in the slide. Okay, so what does the conditional affordance learning model do? So so it has basically, like I mentioned, if you see the affordances here, there are these affordances. So this relative angle and center line distance, these are conditional affordances. Okay, so you see the conditional column here is yes. Okay, why are these conditional affordances? These are conditional affordances because if your next waypoint is trying to take you to the left or to the right, then that information should be available to you at the time of prediction of the relative angle. Otherwise, you will not be able to predict the relative angle. Okay, so you will be able to predict the relative angle conditioned on the next waypoint direction. Okay, so this is what is here. So there are these conditional blocks to which the directional commands go. Okay, and there is a feature extractor. So the feature extractor is a so they use this VGG network. I'm not sure. So you know about the VGG network, but you can use any feature, any generic feature extractor network from the computer vision, and then you can train it further. So so they use the VGG network. Okay, so there is the feature extractor network. Then there is the memory network. So the memory network takes in the last, like in here it is given capital N many frames as input. Okay, so it takes the last N many frames and input, and then it passes them through some kind of a recurrent neural network, and then feeds them to these task blocks. Okay, so there are 6 tasks. So it is a multitask learning problem. So there are 6 tasks, one corresponding to each affordance. Okay, and these 6 tasks are sort of yeah. So these are the tasks that are predicted, and then there are these affordances are yeah. So basically, they go into the controller for the longitudinal and the lateral control. Okay, and these task blocks are basically feed-forward layers. Okay, so we have played around with it, but typically these are like 2-layer feed-forward networks, and with some thousands of nodes in the hidden layer. Okay, and yeah. Okay, and now how does the controller predict the affordance? So there is the longitudinal controller. Okay, so so basically it takes yeah, so it takes basically this affordances, and it has this logic that if hazard stop is true, then you brake. Okay, if red light is true, then you brake. Okay, if the current speed is greater than speed limit minus 15, then you predict this over limit, and accordingly there is a feedback controller which basically applies the brake. Okay, and yeah, so and if your vehicle distance is less than 35, then it goes into this following mode. Okay, and there basically it again applies the brake. Okay, otherwise it is just in cruising mode, so it keeps applying throttle to maintain the current speed. So it is something like this. Okay, okay, and this lateral controller is again a PID controller. Okay, so it takes the center line distance and the relative angle. Okay, and it generates the steer angle which is required to achieve the center line distance and the relative angle. Okay, so yeah. Okay, so okay, so now some results. So we collected about 30,000 frames, and then out of that we collected these keyframes, and there are about 6,000 of them. Okay, and basically our test set is 7,000 frames. Okay, and so our job is basically to measure the performance of our prediction model on all these tasks. Okay, so these are the accuracies that we give. Okay, and these are the yeah, so these are the accuracies on the selected subset. Okay, so subset selection is performed using the technique that we mentioned earlier. Okay, okay, and yeah, so this is kind of so there are 2 things that I want to mention here. This is kind of an ongoing work, so it is under submission. So we have done a lot more things here. So I'm not mentioning any more results. But there are two main problems. One is when we reduce the when we reduce the what do I call the uh, the set of frames. Okay, you remember this. Let me show you this. So remember there is a memory. Okay, so your prediction now depends on not only the current frame but also the previous frames. Okay, and if you don't reduce the data set, then your frames are at constant interval, at constant sampling rate. Okay, uh, and then if you so then you can do like a much so you have more consistent information for prediction of the affordances. Okay, but if you reduce some of the frames and then if you drop some of them, uh, that may no longer be true. Okay, so that is number one problem. And for that, what we have done is we have designed something called cal with timestamps. So it works slightly better, but we are not too happy with it, and it is not yet published. So we have put the results here. So it works slightly better, but not too much better. And it is basically just that you give a timestamp weighted feature as input in addition to the actual features. Okay, so this is one problem that we are facing. The other problem is that it is a multitask approach actually. So you have many tasks and you have loss corresponding to each of these tasks. Okay, so how to give importance to each of these? So that is the second problem for selecting, which is not there in case of selection for semantic segmentation. Okay, so that is all I had. I don't know why this is. Okay. So, okay. So I will just stop here. I think we are out of time, right? So this was the next set of things that I wanted to discuss. But I think we will stop here. And if there are any questions, so I would really like to have a discussion and questions.
Thank you, sir, for the wonderful lecture. And we will see that if any questions are there on chat box. If anybody is having any question, please you can put your question in chat box, or you can put your audio on and you can just ask question.
Okay, Shanti Maiti is asking, can route planning be linked as a routing algorithm like wireless network? Yes. So I think in the there is a field in this robotics called planning and navigation. Okay. So I'm not an expert on that, but so we have done one work. So it is. I think there is a. It is. I'm not sure it is a routing problem. Maybe it is a routing problem. Uh, so there, basically, what you do is you have to generate an exploration mechanism. Okay, so so it also depends on route planning where actually. So if it is, so there are two levels of route planning, right? So one is that you have the road network and then you want to go from one point to the other. So which roads do you want to take? So that is one level. But also inside the road, there may be some obstacle in front of you. Okay, so you may have to take the other lane. Okay, or go to a little bit to the right or a little bit to the left. Okay, so that is part of this exploration approach. And you can check out, so there is this called RR trees algorithm, which are basically robot motion planning algorithms, which can also be used there. But I think just for if you are thinking of it as something like what Google Map generates, like you give a origin and a destination and it will tell you a route through a robot network, maybe that can be solved as a routing problem. Maybe so. So thank you, Hirak Maitri Singh. So Shanti Maitri, maybe in the framework for MDP in RL for obstacle handling. Yes, I think yeah. So so there are some works in the RL community for obstacle handling also using Markov decision process. Uh, yes, I am not 100% aware of that, but I have, yeah, I have seen those works also. Okay, so any other questions?
So I think no more questions are coming. We'll just wait for 1 minute if more questions are coming. Otherwise, we will
Okay.
just end. So just
Okay. Okay, thank you very much, everyone, for giving your attention.
thank you, sir, for your wonderful informations which you gave. So if anybody is want to work on this, they will get some idea for the starting of their work. And if any queries they have, they can mail you also. Thank you, sir,
Okay,
for
thank you.
the session. Thank you, sir. And we will just wait for the participants. We will just wait for the next session. The next session will be the lab session. So we'll just wait for some time. Thank you, sir.
Thank you very much. So I will go.